everyone, I'm glad to present our workshop paper for you today. My name is Lea Kohaus, and together with my two colleagues, Nils Wilken and Hanna Stuckenschmidt from the University of Mannheim, I worked on a new approach for goal recognition. Not everyone may be super familiar with goal recognition, so first of all, it just refers to trying to answer the question of what a person's goal is given an incomplete observation sequence and a predefined set of goals. Right now, goal recognition generally makes this assumption that goals are predefined, but as our approach is not very restrictive regarding the notion of goals, a potential addition may even be to first automatically detect the goals. But before we get ahead of ourselves here, let's look at a really simple example of a question that might be posed to a goal recognition algorithm. Here we see a person first washing some tomatoes, then some carrots, and subsequently cutting the tomatoes. Potentially the person will be doing a number of yet unknown actions next. But with the currently existing information, we already want to know what the person's goal is. So for example, it might be reasonable to say that the person is likely making a salad when the set of goals that are predefined entail salad, brownies, eggs, pizza, and sandwich. And this, by the way, is the set of goals that will be used when we evaluate our methods later on. Predicting the goal can be useful, for example, for providing assistance or advice in smart home environments or in logistics. And furthermore, we could also imagine a sort of mutual support between activity recognition and goal recognition. So goal recognition obviously gets informed by activity recognition, as this provides goal recognition with the actions, but with the goal and potentially also a prediction of the next likely steps, goal recognition could also inform activity recognition on which activities are more likely right now. So to make it a little bit more formal, given a set of goals and an observation sequence O consisting of actions A1 to AT, where AT refers to the last action we have observed so far, we try to find the most probable goal G. Well, we're of course not the first to tackle this problem. There are two main approaches to goal recognition, and the most prominent one is the plan recognition as planning approach, or PROP for short. PROP was first introduced by Ramirez and Geffner in 2009 and then refined a year later. The main idea is just to reverse planning. So in planning, as you may know, you have an initial state, you have a goal state, and you have a domain. And in that domain, you describe the objects as existing in an environment and the actions that are possible given certain states and that can themselves change the states. So for example, if you remember the sequence that I showed you before, our environment would consist of three objects, a tomato, a carrot, and a knife, and three actions, taking, washing, and cutting. And initially, the state is that all objects are not taken, not washed, and not cut. Then we may take a tomato, which is only possible because it has not already been taken, and taking the tomato changes the state of the environment to tomato taken, and so on. What is allowed when has to be specified manually in the domain. In general, the whole domain has to be manually specified. And then in planning, the objective is to find a plan leading from the initial to the goal state using the actions as defined in the domain. And then plan recognition as planning, it's the reverse. The objective is to find the most likely goal given an incomplete plan, and the incomplete plan is an incomplete observation sequence. And what is done to achieve this is that a planner is run 2 times per goal, and then obviously produces 2 plans, one plan entailing the observation sequence and one not entailing the observation sequence. Plans have a cost, it's usually just the length of the plan, and the cost difference between these 2 plans then tells you whether the actions observed generally move the state closer to the goal state or not. So for example, if you observe the tomatoes and carrots being washed, and this has to happen to make a salad, then the plan entailing the observation sequence is not costlier than the plan not entailing the observation sequence for that goal of making a salad. And in difference, if we look at achieving the goal of brownies, observing these actions make the plan embedding the observation sequence much costlier than the plan without the observations. So the important thing with prop is that it requires the modeling of a domain. There's manual work and it requires expert knowledge. Furthermore, if something changes, so for example you add a goal or you add an action, pretty intense remodeling is required. And modeling is already a lot of effort as it is. Actually, all papers so far only use artificial data to test their approaches. This means that they don't model domains to work with real observation data, but instead they use predefined domains that have been used by the planning community for a while, and then just use plans generated by the planners as observation sequences. Which also, by the way, means that in difference to humans following a plan, all actions produced are perfectly rational and that they're strictly necessary to achieve that goal. Another problem with prop is that a planner needs to be run 2 times the number of goals, and that makes it really slow. And how slow we'll see later on. So although extensions to prop actually do exist, making it faster, but really not nearly fast enough, none have been evaluated on real data. And maybe even more importantly, they all still rely on domains. And as always, the alternative approach is to use data and to use data-driven methods such as LSTMs or RNNs to predict the goal. Like all data-driven approaches, this requires a lot of data and in this case actually also pretty detailed annotations. And that kind of data, as you can probably imagine, is hard to come by, and there are very few studies out there actually using data-driven approaches, and those that do use it then use artificial data. So the question is whether we can find another approach that works just as well as the others, but that does not require a lot of data, nor a domain, or any other kind of manual modeling effort, and that is close to real time regarding computation. These considerations are the starting point for our approach that we call blend-driven goal recognition. And the intuition for it is to, first of all, not work with all possible plans, as in prop, because planners can theoretically compute all possible plans, but only with a few exemplary plans per goal, and to then compare an incomplete observation sequence against them. And exemplary plans can, for example, be previous observation sequences, plans generated by a planner, or extracted from textual data. So basically everything that leads from an initial state to a goal state. Note though that because we do not use domains, we also no longer rely on actual state definitions. And this allows us a much more relaxed understanding of goals. Furthermore, please note that our plans, depending on the source a little bit, may include superfluous and irrational actions, or maybe even misactions because they have not been recorded. Now, of course, we need to find ways to compare these exemplary plans against the observation sequence. And we came up with a base heuristic and 2 extensions to do it. Generally, we need k exemplary plans per goal, and for the base heuristic, we compare each plan belonging to a goal against the observation sequence, and then divide the overlap of these 2 by the length of the observation sequence. We do this for all plans and compute the maximum overlap across all plans of all goals. Then for each goal, we check how many plans of that goal achieve the maximum overlap, and this gives us our most probable goal. We can then extend this heuristic by considering the order of actions. The assumption here is that many actions can appear in not quite but near arbitrary order, but that the actions containing a specific object appear in a certain order. So for example, it doesn't matter whether you first wash the tomatoes or the carrots, but it probably matters that you wash the tomatoes before you cut them. And the same holds for logistics. It might not matter whether you first load packages A or B, but it matters that you load A before you depart. So what we do is to only count actions in the overlap computation that contain objects which have either not appeared at all before, or that have been handled in the same way. So for example, if the action cut tomato appears, we check whether the object tomato has occurred before in the plan. For example, wash tomatoes may have occurred. So we check whether this action also appears in the observation sequence before. And only then do we count it towards our overlap computation. We have a second extension where we work with the assumption that the frequency in which actions appear may also be important. Some actions may appear frequently across our goals, and others may appear frequently in plans for one goal but not for other goals. Therefore, when we observe an action, this also tells us how relevant it is. In order to use this information, we came up with a measure kind of obviously inspired by TF-IDF. Each action gets assigned a weight, which is computed by dividing the number of plans belonging to a goal containing this action by the number of plans of that goal. So this is actually equivalent to our K. And then we take it times the logarithm of the number of goals divided by the number of goals which have plans entailing the action. This then of course also changes the overlap computation. We now sum over the weights of the overlapping actions and divide by the sum of the action weights in the observation sequence. Remember that before we just used the number of elements appearing in both and divided it by the length of the observation sequence. So now that we've talked about our method, I want to briefly talk about how we evaluated it. Pretty obviously, we compared the accuracy and the computation time of our methods with varying K. So just as a quick reminder, K refers to the number of exemplary plans per goal. We also vary the observation length, and then we compare it against the results of prop. With varying observation length, we mean that we take the first 5, 10, 15, and so on % of actions of the observation sequence and then try to find the goals based on that. We evaluate our method on two different datasets. The first one, logistics, is one of the datasets typically used to evaluate prop approaches. There are no real observations in logistics, it's really only a domain, and then typically observation sequences are generated by simply running the planner over and over again. And in order to make it a bit more realistic, as we should usually expect actual humans to not act perfectly rational, but plans generated by a planner will only contain actions strictly necessary to achieve a goal, so they will be perfectly rational. We always either pick the next action proposed by the planner or an arbitrarily currently possible action, just by chance. And logistics then contains 20 goals and is made up of relatively short observation sequences. We additionally used the CMU kitchen data. This one contains real observation data of different people cooking 5 different recipes in the kitchen. It only contains 5 goals with very differing average observation lengths per goal, reaching from 57.9 to 111.2. In order to evaluate prop on this, we of course had to model our own domain, and yes, this was actually a lot of work. One final note on the evaluation, we used case sequences per goal as example plans, and then of course a different sequence to predict on. Okay, so now let's start discussing our results. We'll start with the logistics data. On the left-hand side, we have the base heuristic with different numbers of K, and in comparison to prop is the purple dotted line. Prop achieves similar levels of accuracy as our approach, with either very few observations or when the sequence is almost complete, but in between our approach outperforms it. Note that this is actually quite remarkable because the observations themselves were generated with the same planner that prop then also uses to recognize the goal. And regarding the different values of K that we've used, we can see that although K equal to 3 performs slightly worse than the other values of K, the difference is actually not huge, meaning that this works even with a small number of exemplary plans. On the right-hand side, we see the results for the base heuristic. the ordering and the uniqueness extensions, and again the difference is not large, but for the uniqueness extension it seems that the accuracy is a little bit unstable. Now we have the CMU data, and here we see the base heuristic and the two extensions on the left hand side. Very similar to the logistics data, the difference among our approaches are not huge, but here the two extensions seem to provide a bit more stability, and particularly later on. And all methods, and I guess that's the most important thing, clearly outperform prop. Again, prop is the purple line. That prop works so poorly, especially later on, has to do with it regularly reaching our timeout, which we set to 3 minutes. And note that although the extensions do not appear to perform much better than the base heuristic, we think they might provide clearer benefits in more large-scale settings. The right-hand side shows the different k's again, and there's barely a difference. Even k equal to 3 is really not that bad. And that's great news, because it means our approach requires very little previous data. Okay, finally, let's have a look at the average computation time. In this graph, you can see a comparison of prop's computation time on either dataset and our approach's computation time with a k equal to 29 on the CMU dataset. Note that using a k of 29 is even the costliest setting that we have. And it's easy to spot that prop doesn't even work in real time for the artificial logistics data, and for CMU, it's completely out of bounds. So our approach is really fast in comparison, generally below a second. So to conclude, we can say that our approach works very well, while at the same time it ticks all the boxes of the criteria we defined before. It requires only a little amount of data, no manual modeling effort, and is really close to real time. So now that we've established this, we can move on to new questions and projects, because this is really just the first step. So our first idea is to extract plans from textual data and test the approach on a large-scale setting. Because technically, a very large number of plans, for example for cooking, already exists in the form of recipes. The only thing we need to do is to extract the actions, and then we can scale up evaluation. Furthermore, as our approach has a more relaxed notion on goals, we could also try to automatically extract them. This could work really well with our idea of goals and actions and how they are interrelated. A further natural extension is to now start predicting the next action or next actions, and this could also be used to assist with activity recognition, as I've mentioned right at the start, which means that we've now come full circle. So thank you for your attention and your interest. I'm really looking forward to hear your thoughts.